All right, 2.3 is all about functions and math models. So we're going to be working on some applications here, also known as word problems. But bear in mind, these are the type of applications we're only going to be doing with algebra today. You're going to be seeing a lot of these same concepts in later chapters, but using calculus. So today, again, just still laying that foundation. Today, we're going to solve application problems involving functions. Most of them are going to be linear functions. You will see at some point a quadratic function that will result from some data that we're working with. So first example, consider the following graph about the number of active Facebook users. While the data do not fall in a perfect line, it's nearly linear. Thus, consider the line drawn on the graph below or to the right, which approximates the actual data. All right, so there's a lot of information here. You will be able to see this a little bit more clearly on your notes, but you're given actually 2 points here on the graph. They're kind of light, so they're a little bit hard to see, but they're gray. And there's one point right here. I'm going to go ahead and just kind of fill this out on mine so I can see where that is located. And then I'll fill this one out. Okay. You can see here that the graph has months of the year starting. In this case, it looks like the first month that's labeled is March of 2009, and then heading up through December of 2012. You can also see the y-axis up here. The vertical axis is users in millions. So it's important to note that obviously there weren't only 200 users. So it matters. A lot of times you're going to see these application problems, and just the number isn't always necessarily the answer. A lot of times your unit will be given to you either in millions or in thousands or something like that. So make sure you pay attention to that. I've had students in the past who are like, I don't get what's like this WebAssign isn't accepting my answer. I can't figure out why. I'm like, oh, well, you needed to multiply it by 1,000 because you just answered for whatever you solved for X. So they had it right. They just didn't consider that in their unit. So something to think about. All right, we're going to let Y be the number of users in millions, and the X will be the months after December of 2008. So you can kind of see here off to the side, we have information about these different values of X, like X equals 1 will correspond to January 2009 because that would be 1 month after December 2008, so on and so forth. Sorry, I didn't give myself enough leeway on my document camera. Let's see. This there. There you go. It's a little bit better. I can move this guy around. All right. Awesome. So first, we're going to find and interpret the slope in practical terms of the problem. Now, one thing you might want to note right away is that this line is very clearly going up from left to right. So you're expecting the slope is going to be positive. Earlier, we had discussed depreciation of a machine 2 sections ago. And because it was depreciating, we saw that that value was going down from left to right. This is the opposite situation. So we're expecting the slope is going to be positive because the number of users over time is increasing. So we're going to find and interpret that slope in practical terms of this problem. In order to do that, remember that to find a slope, I need 2 points. I'm going to remind you of that slope formula. So we need y sub 2 minus y sub 1, so the change in y over the change in x. In order to get values for these coordinates, I need to actually just figure out what these correspond to on our graph. Now, I can go ahead and note that if I go directly down towards the x-axis from these points that we already found, these points, by the way, are given to you because they're really clear-cut values on particular nice numbers, hundreds of users and millions. So if I draw this one vertically down, it'll take me to this data point at March of 2009. And if I draw this one vertically down, it's going to take me about, the best you can, to December of 2010. So what I need to do is figure out what values these actually give me as ordered pairs, because I need an ordered pair for x comma y for each of these. Now remember that x represents months after December 2008. if our first data point is occurring in March of 2009, well, this we're being led to the conclusion here that in that case, X would have to be 3, because January 2009 would be 1 month after December 2008, so on and so forth. So after February would become March of 2009. So that would be X equals 3. So we can go ahead and write this ordered pair on the graph. And then the Y coordinate would be just the number of users in millions. So we're just going to leave the unit as it exists on the graph, which is 200 on the Y-axis. So our first point will be 3, 200. Now, again, you don't have to label these. I'm probably just going to call this 1, just so that I can say that 3 will be X sub 1 and 200 will be Y sub 1. Now, this will be 0.2 for us. This one's a little bit trickier because now we need to figure out what value of X would correspond to December of 2010. But the nice thing is you were given information about December of 2008. So we can kind of go from one December to the next. So if X equals 1 in January of 2009 and X is months after December 2008, well, that must mean that X equals 0 corresponds to December 2008. So if I'm trying to get up to December of 2010 to figure out the X value for this data point, well, I know that I'm going to take 0 plus 12 more months gets me up to December of 2009. Plus another 12 months will get me up to December of 2010. So the 0 is the December of 2008. So if we accidentally thought that X was measured in years, we'd have a problem here with being able to find these correct values. So it's really important that we understand that X is just months after December 2008. And you're going to see a lot of variables defined this way, where you're just sort of comparing it like the value after this amount of time. So this is a very common way of defining our variables. All right, so that will be 0.2 for us. We are going to say that it is 24. So I have 24 months after December 2008 would be December 2010. And then I'm going to go ahead and take the Y coordinate, which in this case is 600. So now I have 24, 600, and that will be the coordinates for 0.2. So to find the slope, I now have the 2 pieces of information I need. I have the coordinates for X sub 1, Y sub 1, and X sub 2, Y sub 2. All right, so I'm going to take my Y sub 2, which will be the Y coordinate of the second point, minus Y sub 1, which will be, in this case, 200, divided by X sub 2 minus X sub 1. And then we'll simplify. I'm going to leave this 2 ways. First, I'm going to leave an exact answer that's just written as a fraction. And then so that we can interpret the slope in practical terms, we'll turn it into a decimal. So another thing is, if you wrote the points in the opposite order, if you let this be 0.1 and that be 0.2, that's okay. You're just going to get a negative divided by a negative, which will just turn out to be a positive. So you'll get the same answer regardless. So 600 minus 200 is going to be 400. And then 24 minus 3 is 21. And when you put that into your calculator, 400 divided by 21 is approximately 19.05-ish for the slope. So remember, the slope is the change in Y over the change in X. And as long as you remember that, well, you know that Y represents users in millions, and then X represents months after 2008. So when we're trying to figure out what this slope means in terms of some sort of practical value, we would say that the number of Facebook users is increasing at a rate of 19.05-ish, so of about 19.05 million users per month, because remember, X is measured in months and Y is measured in millions of users. So millions of users per month. So it's positive value, it's increasing. The slope is positive. We would just make that statement, which I think is pretty intuitive for us. All right, so now that we have the slope, we're being asked to find the linear function. We're going to be doing this all the time. So the note here is remembering how to find the equation of a line will be crucial throughout this course. Yes, we're going to be doing it in literally every single chapter. So I'm going to remind you, if you don't remember how to find the equation of a line, there are a few different ways of doing this. The one I like to use is just the point slope formula. I always like to tell my students, you need two different quantities in order to write the equation of a line. You need a point and a slope, which is why I like to use point slope form. So point slope form is going to be y minus y sub 1. Here, I'll write here. Point slope form y minus y sub 1 is m times x minus x sub 1. Now, if you're like, oh my gosh, how would I ever possibly remember this for my test? Well, if you remember the slope formula, this is basically just the slope formula all over again. If you multiply both sides of the equation by x sub 2 minus x sub 1, and then in this case, your point x sub 2, y sub 2 is just some general point xy. So it's the same exact thing. All right, so in order to get this equation of our linear function, I need the slope, which I already have, and then I just need to pick one coordinate that I'm going to use. Pick a point for x sub 1, y sub 1. You decide. You have two ordered pairs you could use. I'm going to use the ordered pair that has the smaller values in it. I know this isn't that different, but if I'm going to be working with numbers, usually I just like for them to be a little bit smaller so I don't need to worry about anything. I don't know. In this problem, it's not really going to make much difference, but oh well. All right, so I'm going to leave y as just y minus y sub 1. So I'm going to pick the point 3, 200. So my y sub 1 is going to be 200 equals m. Now, this is a point of contention for a lot of people. I'm going to leave my slope exact right now, and I'm going to round it at the way end. I hate to have rounding errors in my problem, and if we do too much rounding in the process of finding our answer, we could be off by some digits. So I'm going to leave this exact for now. We approximated this to 19.05. In this particular case, it's really not going to make a difference, but I want you to get into the habit of carrying around exact values and rounding at the end. So that's your slope. And then x minus x sub 1. So x minus 3. And then we'll just go ahead and solve for y. Solve for y. Offset that. So I'm going to say that we have y equals, and then I'm going to distribute this 400 over 21 into my parentheses. You should already have this value in your calculator, though, because you literally just found this. So I'm going to multiply it by 3. So we'll say minus. You know what? I multiplied mine by 3, and then I left it as a decimal, which is fine. But I want to turn this into a fraction just for now. So I'm going to say math, enter, enter. Oh, you can't see that at all. It's 400 over 7. Where's my whiteout pen? I don't know. I'll find it. Don't worry. 400 over 7 is going to be that quantity. And then we still have to add this 200 from the other side. So in this step, we distributed the fraction into the parentheses. And then we added 200. And the last thing we need to do is just simplify these coefficients just by adding them together. So I'm going to multiply my answer here by -1 because it's a minus. And then I'm going to add 200 to it. And then my calculator, if I already asked for a fraction, is going to keep giving me fractions. But I'm going to now just turn that into a decimal. And if I want a decimal, I'll do math number 2, enter. And then it'll give me a decimal approximation. So when you put this into your calculator, you will get the same decimal we got before, 19.05 x, and then we'll have, let's see, we had negative 400 over 7 plus 200. I get plus 142.86. Now, two things here. One thing I was going to mention is, even though I like to have students use point slope form to find the equation of a line, a lot of students in algebra learn to use the method where you use y equals mx plus b, and you plug in y and x and m, and you solve for b. That's fine. If you want to do it the method of solving for b, that's okay. What you'd be getting is this quantity. So b is the y-intercept. Y-intercept. And this should make sense to you on the graph. You should see this crossing the y-axis at about 142.86. And you do indeed see that behavior. So if that's 200, this would be 100. I mean, it doesn't look quite there, but remember, these data points are just approximations. I mean, this is just a line that sort of fits what's happening with the data. It's not quite exact, but it's saying that we're getting this value to cross the y-axis at about 142, which looks good. So it's about halfway between there, between those two values. So those were the two things I wanted to say about your y-intercept. So pay attention to the rounding instructions that you get in WebAssign so that you know how far to go with your rounding. All right, we're going to continue using this function for a couple more minutes. For part C, oh, I'm not double-sided. Part C. Using the linear function, how many active Facebook users would you estimate there were in January 2009? All right, so the idea here is we found a function, and once we ended up writing our own function, now we're going to use it. So I'm going to remind you of what the function was that we just found. It was y equals 19.05x plus 142.86. So this will tell you the number of Facebook users in millions given a value for the number of months after December 2008. So using the linear function, how many active Facebook users would you estimate there were in January of 2009? Well, we need to figure out the value of x for January of 2009. And then once we find that value of x, we can substitute it for x in our function and figure out the number of Facebook users. So that represents y. All right, so we know that if x equals 0, oh, you know what? I have a note to self here to change this to January 2013. Do you know why? Because if it's January 2009, then x equals 1, and it's a very boring problem. Let's change this to 2013. That's better. Okay, so I just said that January 2009 was x equals 1 because it's 1 month after December 2008. And again, we had this on our first sheet where we were kind of talking about that. January 2009 is x equals 1. So if we know that x equals 1 is January of 2009, well, we're going to use the same process where we just add 12 months, add 12 months, add 12 months in order to get to January 2013. So x equals, well, 12 months later, 1 plus 12 is 13, gets you to January of 2010. Add 12 more, and you'll get to January of 2011. Add 12 more, and you'll get to January of 2012. And then add 12 more, and you'll get to January of 2013. So we're just going to keep adding 12 months to get to the next exact year. And now we know that x is going to be 49. So that was the hard part. Now all we have to do is just evaluate our function for x equals 49. So we'll say that y equals 19.05 times 49 plus 142.86. And you're going to put that into your calculator. You already have some decimals here, so We can go ahead and just leave those. So we have 19.05 times 49 plus 142.86, and I get 1,076.31. I'm putting an approximately equal sign here because these are rounded values that I used. Okay. So if you're not really thinking about what this means, then you're going to put a box around the answer and move on. Do you think there were 1,000 Facebook users in January of 2013? I don't think so. There were a lot more. Trust me, I know. I probably knew like 1,000 Facebook users in January 13. It was wild. I used to be a student at ECC, and when I transferred to U of I, the coolest thing was that I got to have a Facebook account because we didn't have school email addresses at ECC at the time, and you had to have a school.edu address to get a Facebook account. Did you guys know that? It's true. You couldn't just get a Facebook account. You had to be affiliated with the university with the .edu address. Yeah, it's crazy times, crazy, crazy. And now you guys don't even want Facebook accounts. You're over it. All right, so we know there weren't 1,000 users. So you have to go back and remember what Y actually represents. It's users in millions. So 1,076 million users. I guess that's okay. Personally, I don't usually say 1,000 million. My kids say 1,000 million, 1,000 million billion. Remember that this really represents, if we're talking about millions. Okay, so this would be the number of millions that we have, which would look like that. Now, oh gosh, I forgot the 0.31. Where's that whiteout pen when I need it? So it looks kind of like this, and this would actually be in billions. So this would be your millions, and these would be your billions. So you could say that's 1.08 billion approximately. I'm not going to be too big of a stickler on that. I probably wouldn't put something on a test where I would force you to change millions to billions, but this answer technically has more digits in it. All right. Part D, using the linear function, when, this indicates time, would you estimate that the number of active Facebook users will reach 1,100 million? The number of Facebook users is going to be represented by the variable Y. Now, this is given to you in millions, so you can go ahead and just use this number for Y because Y is represented by millions already. All right, so when, we're going to have to solve for X. So this time we're going to use our model, and we're going to let 1,100 be Y. And then we'll say it's 19.05X plus 142.86. And then we'll solve for X. I'm going to subtract 142.86 from both sides. I feel like my calculator showed up a little bit better in the last lesson. You know what? I was using a different calculator. I thought it has something to do with my brightness. It's better. Okay. 1,100 minus 142.86. No, not that. 0.86 is 957.14, which is 19.05x. Now I'll divide both sides by 19.05. And hopefully we'll get an answer that makes sense. We'll get x is approximately equal to 50.24 months. X represents the number of months after December 2008. So again, if you just got an answer of x equals 50.24, you'd be like, okay. You got to remember what x actually represents. It's months after December 2008. So we can figure out what that is. Let's see. 50 would be, oh, wait, we got this here. 50 would be February of 2013 because we already found 49. So 50 would be February of 2013. And then 51 would be March of 2013. Oh, sorry, I'm writing and you can't see. X is 50, that corresponds to February, and then x equals 51 is March. So it's going to happen at some point. This will happen at some point between February and March of 2013. That's your estimate. And you can look and see if that makes sense, although your graph only really goes up to December of 2012 right here. But you're looking at when you think it's going to hit 1100, which is this quantity right up here. And yeah, you would think that that happens pretty soon after December of 2012. So it's just an estimate based on the model that we created from this graph using the slope and some points we knew on the graph. So there's a lot we can do if we can approximate a line to some data points. And, you know, of course, the growth of Facebook is not exactly linear, but it looks close to that shape. I don't know if you did any work in stats or college algebra with fitting lines to data or fitting curves to data, but this data is looks like it's pretty close to a linear fit. So we can use that fact to write linear equations and work with those equations to talk about what's happening with the data. So it's pretty cool. Okay, one thing that you're going to see a little bit of are geometric applications here. You're not going to see a ton of it, but a little bit. And you should have done stuff like this in your algebra classes previously. A rectangular garden is to be planted with an area of 4,000 square yards and to be fenced on all four sides. Express the number of yards of fencing as a function of the longer side, x. So you're being told here that x is the longer side. So if you're going to be, I always recommend with geometric problems that students sort of just make a little drawing to correspond to the data. But it's a rectangular garden. So we're making a rectangle. Doesn't have to be anything super fancy. And we're being told that the longer side is x. Usually we just write the other side as y. You can come up with any variable you'd like, but we'll just call it y. The area is 4,000 square yards. That's important. We need to talk now about the area of a rectangle, so we're going to start writing equations here. The area of a rectangle is x times y, length times width. So the area of a rectangle is length times width. And in our case, we have these labeled as x times y. You know, I used an x right here, and I totally didn't mean to because I have an x in my problem. Well, it is what it is. We'll call it a circle. Do whatever you want to do with that. So I'm going to take the length times the width. You call either one either thing. I usually think of the width as going from left to right, but that's up to you. So this will be x times y equals 4,000 is an equation that would represent the area. We're also being told that this rectangular garden is to be fenced on all four sides. Express the number of yards of fencing as a function of the longer side, x. Now, the number of yards of fencing doesn't have to do with the area, because remember, the area is talking about the space that is covered by the inside of the rectangle. When we're talking about fencing the rectangle, we're talking about perimeter. We're going to be laying fence around all four sides. I'm going to need X units of fencing on each of these two longer sides, and then I'm going to need Y units of fencing on the other side. So let's see. I'm going to go ahead and express the number of yards of fencing as a function of the longer side, X. So we can, if you would like to label these variables, maybe you could say we're going to let, we probably should have done this first, but I did not. I don't know why. Let X and Y represent number of yards of fencing. Okay. So if I'm going to be fencing this, I'm talking about perimeter. I'm just going to add X plus Y plus Y to get the number of total yards of fencing that I'm going to need. What we're going to do is we're going to express this as a function of X. So instead of just saying this is the perimeter, I'm going to say, okay, this is some function of X. It's 2X plus 2Y. And if you're like, wait a second, this isn't necessarily a function of X, you're absolutely right. It's not. There's a reason we have this information. If I'm going to write a function of X, I need all the variables in that function to be X. Otherwise, I have a function in two variables, which is more of a Cal 3 situation. In order to get Y, I'm going to go ahead and use this quantity that I already have that relates X and Y in a different way. If I know that X times Y equals 4,000, then I know that Y is 4,000 divided by X. So I'm going to have to substitute that in so I can get this function written only in terms of X. So here's my function. If you want to call it f of X, that's fine. You could even call it P of X. Maybe I'll call it P of X since it's perimeter. We'll have 2X plus 2 times, and then this is where we'll substitute this value in for Y, 4,000 over X. And then we'll just simplify. So P of X is 2X plus 8,000 over X. And that's it. That's a function for the perimeter written in terms of X. So like I said, you should have seen a lot of this type of thing when you were solving systems of equations back in your Algebra 2 class or maybe Algebra 1. I know it's been a while, but there's a reason you're given two different pieces of information, and that's so that you can sort of use them in conjunction with each other and make a substitution. All right. Now we're going to shift gears into talking about supply and demand. This is not an economics class. I'm not an economics professor. We're just going to be talking about basic supply and demand, which is going to be really important to you anyway if you are working in the business world. Maybe, maybe not. I don't know. Supply and demand. So I'm going to give you just some graphs so you can get a general idea of what's occurring here. But for the supply function, you're going to consider this from the supplier's perspective. And then for the demand function, you're going to consider this from the consumer's perspective. I think if you think about them in these ways, it really helps you to understand what's actually going on with these functions. And again, you will see these again in later chapters. We're just sort of introducing them right now. For the supply curve, it kind of looks like this. And usually we'll just label it with something. You can call it S of X. A lot of times it'll just be called Y, or maybe it'll be called P. The reasoning behind this is because from a supplier's perspective, the more units you supply, the more your price is going to go up for what you are going to have to dish out to make those units. Does that make sense? So as you produce more units, your price is going to be going up. So the amount that you're going to have to spend making those units. Now for the demand function, and I think maybe the demand function is a little bit easier for everyone to understand because we have a lot of experience being consumers, whereas most of us don't have experience being suppliers. It's going to do the opposite. So as the price goes down, the demand goes up. It makes sense. Maybe there was something you wanted to buy, but it was too expensive. Well, now the price goes down and everybody wants it because now it's more affordable, more attainable. Whereas if there was something you wanted and now it's like a lot more expensive, you're much less likely to buy that item because either you can't afford it or maybe it's not worth it to you. I was thinking about eggs, but we don't have to have eggs, but definitely I think a little bit more about the things that I purchase now. The things are a little bit more expensive. Like, do we really need this? Do we really need to be eating this every day? Like, this is like a really expensive item. Or maybe even things like cars. I mean, the price has just gone up so much, especially for used cars. So maybe people are kind of like, well, do I need to buy a new car right now? The price is going up, but I don't know if the demand is actually going down for that. Maybe it's not working the same way. Well, something happens here where the price was going to settle at an equilibrium point where the quantity X, which is the equilibrium quantity, and the price, the equilibrium price, are the same. So the equilibrium occurs when the supply equals the demand. We're going to be talking a little bit about equilibriums here as well, and just sort of getting used to these supply and demand equations. So here's what a problem like this is going to look like. We're going to let the supply equation be P equals negative X squared minus 2X plus 100, where X is the quantity supplied in units of thousands. When you come across important information like this, where you feel like, oh, I might need this later and forget about it, put a box around it or something, call it out. And P is the unit price in dollars. The demand equation is P equals 8X plus 25, where X is in units of thousands again, and P is the price in dollars. Okay, so same idea, units of thousands. What unit price would induce the supplier to make 8,000 units available in the market? All right, so 8,000 units, well, X is the quantity supplied in thousands of units. So X would be 8. We also need to think about the fact that we're talking about the supplier here. You were given two different equations with a P equals, but since we're talking about supplier, we're going to look at that supply equation. So we're going to focus on that one first. I already know that X equals 8. So what I'm going to figure out now is the unit price. This is the question. Whenever there's a question, that's what leads you to what variable you need to find. So we're going to say P equals, I'm going to take this price or this equation here for the supply equation, and we're just going to let X be 8. So I'm going to say negative, and then we'll take 8 squared minus 2 times 8 plus 100. Now, by the way, I know I did this and it was very subtle. I said 8,000 units, X equals 8. That makes a really big difference because that's massively going to change the price. If you plug in 8,000, square it and make it negative, and then you plug in another 8,000, that's going to really send this price into some crazy amount. So be really careful with that. It's actually going to be a negative amount because you'd be squaring this and then making it negative. So you'd probably end up getting a negative quantity. maybe not. And then you'd be like, wait a second, that can't be right. Let's see, you'd get negative 64 minus 16 plus 100. Oh, no, you'd get 20. Oh, well, either way. Oh, no, sorry. Ignore that. I need to stop saying things without writing them down. Negative 64 minus 16 plus 100. When you put this into your calculator, you get $20. So that is the unit price that would induce a supplier to make 8,000 units available in the market. I know what I was trying to say was if you accidentally did 8,000 instead of 8, you'd have negative 8,000 squared minus 16 times 8,000 plus 100, and you'd get this for your price. And you'd be like, whoa, this doesn't look right to me. I hope you would say this doesn't look right to me. That would be crazy. So then you would know, like, this doesn't look right. Something's going on. Just something to look out for, making sure that you get that right value for X. Okay, so $20. Find the equilibrium quantity and price. So when I'm finding the equilibrium, I'm finding the place where those two are equal, the supply and the demand. So I'm going to take the supplier equation and set it equal to the demand equation. And then you have to solve this equation. Well, the equation's quadratic. Anytime we're trying to solve a quadratic equation, we want to get all the variables and all the constants on one side, and we want to have it set equal to 0. Now, I like to have a positive coefficient on the squared term, so I'm going to move everything over to the other side. So I'm going to add x squared. I'm going to add 2x, and I'm going to subtract 100 just so I can get this set equal to 0. So I'm just undoing all these operations on the left-hand side. And now I have 0 equals 10x minus 75 plus x squared. Now, if this isn't screaming anything out at you, rearrange it so it's in descending order. And sometimes even just having the equal 0 on the right instead of the left makes a difference when you're thinking about what you should do. So I'm going to rewrite this as x squared plus 10x minus 75 equals 0. Now, I'm going to solve this by factoring. You can always use the quadratic equation. It always works every time. But if you can factor it, factor it. So I'm thinking about numbers that multiply to give me negative 75. You can technically use the AC method, but you don't have to here because your lead coefficient is 1, which means you can do AC, but it's unnecessary. All right, so I know, for instance, that if I multiply negative, let's see, I'm thinking 15 and 5, some combination. Let's make the 5 negative and the 15 positive. I can multiply these two together. I'll get to negative 75. If I add them together, I'll get to positive 10. So let's go ahead now and factor this. So I can say that this is x plus 15 times x minus 5 equals 0. And then I'll just use that 0 factor property to say that x equals 5 or x equals negative 15. Now, I don't want you to automatically just get rid of any negative value that you obtain. But in this case, you need to remember that x represents a quantity of units in thousands. You can't make a negative quantity of items. Therefore, we're going to eliminate this as a possibility. And we'll just say that x equals 5. Now, I put a box around it, but that doesn't mean I'm done. I need to find the equilibrium quantity and price. This leads me to the quantity. Remember that x is in units in thousands. So if I was talking about 8,000 units, I said that x was 8. So if x equals 5, this means 5,000 units. Once I have that, though, I need to go ahead still and keep this x to find the equilibrium price. Now, if you're trying to go back and solve for p, you know that these two equations are equal at this point. So you can choose either one when you're solving what really is just this system of equations. So this is going to work for both equations and make them true at this equilibrium quantity. So I'm just going to go ahead and use P equals, you pick the equation. I'm going to pick P equals 8x plus 25, and I'm going to use that with x equals 5. So I'm going to say that this is 8 times 5 plus 25, and I'm going to get P equals $65. So I know we have x equals 5. Our answer is officially 5,000 units and $65. Equilibrium, price, and quantity. The last thing in this section is just another problem that's talking about finance, of course. New problem, number 5. If 10,000 bottles of wine are produced, profit is $5 per bottle. If more than 10,000 bottles are produced, profit of the entire lot drops by 0.0002 cents for each additional, or $0.0002 for each additional bottle sold. Assume at least 10,000 bottles are produced and sold. Let X be the number of bottles produced and sold over 10,000. Find the profit function. Now, this is a little tricky. This is one of those questions where, like, once you see it, it's like, oh, duh. But until you see it, it's kind of hard to figure out. Now, you might initially be thinking like, oh, well, profit function. We just talked about profit function in the last lesson. We did talk about profit function. Now, usually, and this is what we did in the last lesson, we would say that the profit function is just the revenues minus the costs. We take the amount of money that we generate by selling these items, and we subtract off the cost of us making these items. In this case, though, you know nothing about the revenue, and you know nothing about the cost. All you know about is just the profit and how the profit relates to the number of bottles that are sold. So this one's a little bit trickier. So what you're going to have to do here in order to come up with your profit equation is you're going to have to take the profit in dollars per bottle, and you're going to have to multiply that by the number of bottles. If you guys have taken chemistry, you've done something called dimensional analysis, where you sort of canceled out units. If you have bottles in the denominator and here bottles are in the numerator, you just cancel the bottles out, and all that leaves you with is profit. So you can always play around with your units like that if you need to. Once you know this, though, we're still going to have to come up with some quantities with variables that tell us something about the profit per bottle and the number of bottles. You were already told in the problem statement that X is going to be the number of bottles produced and sold over 10,000. So for the number of bottles, you know that it says assume you're making at least 10,000 of them. If you're making at least 10,000, you're also making X more than that. That's going to give you the number of bottles that you're making total. So we can talk about number of bottles by saying, okay, we know we're making at least 10,000 of them. And then we're adding X more of them. So we're producing and selling over 10,000, this amount X. So this will represent the total number of bottles produced and sold. Now you just need to figure out the profit per bottle. Well, you were told initially that if there are 10,000 bottles produced and sold, the profit is $5 per bottle. But now you're being told, assume at least 10,000 are produced and sold. So there's going to be more than that. if more than 10,000 bottles are produced, profit of the entire lot drops by $0.0002 for each bottle sold. So we're going to think about this here as like, okay, the profit would be $5 a bottle. But we have to take away this dollar amount for each additional bottle. And each additional bottle is represented by the variable X. I know I put some dollar signs on here. Sorry if that's throwing you off. You're just being told, though, to find the profit function. This is probably okay if you were entering something like this into WebAssign. You might be told to leave off the dollar signs. So this would, as a function, would look like this without the dollar signs. So it's 5 minus 0.0002x, and then multiply that by 10,000 plus x. So I think when you break it down to these components and kind of talk your way through it, it's like, okay, yes, this makes sense. But again, it's something where if you have to come up with it on your own, it can be a little bit challenging. I know for a fact that there's one example that looks kind of like this that you're going to see down the road, and I'm going to remind you of this problem when we get to it. So you might have to use this level of thinking again. But you know that the profit is just going to be the profit per bottle times the number of bottles. I mean, it kind of makes sense. I mean, you can think about it if you were selling stuff like lemonade. If you ever had a lemonade stand when you were a kid, you know, you charged 50 cents per cup. Well, you knew what your profit was going to be if you knew how many cups you sold. You'd be like, all right, well, 50 cents per cup times I just sold 20 cups, and you knew you made 10 bucks. It's the same idea. It just sounds more complicated because there's a lot of information that's happening here. Last question, if 16,000 bottles are produced and sold, what is the profit? Well, you have a profit function. So you're just going to find P of, oh, not 16,000. Ooh. X is the number of bottles produced and sold over 10,000. So the number of bottles produced and sold over 10,000 is actually 6,000. Number produced, sold over 10,000. So to get to the 6,000, we had 10,000, or actually 16,000 minus 10,000 equals 6,000. And then we'll evaluate P of X, which is P of 6,000. See, that one almost got me. It can be tricky trying to figure out exactly what variable are we looking at and exactly what does it represent. All right, so P of 6,000, I'm going to put this into my calculator. Let's see, 5 minus 0.0002 times 6,000 times 10,000 plus 6,000. What? Oh, I forgot a parenthesis. Ooh. Let's pull that back up. $60,800. So that's just using that function that we already wrote. All right. Now, you can, of course, get some sort of an estimate for this. Like, let's say you were like, well, I know profit's going to be about $5 a bottle. And if you don't think about the fact that the profit drops per each additional bottle sold, if you just said like, okay, well, it's about $5 per bottle times 16,000 bottles, it would be 80,000. Wow, that's like quite a big drop in profit when you think about it. I mean, this doesn't seem like a very big change. But if you took $5 a bottle times 16,000 bottles, you would get 80,000. So that's a big profit loss. It doesn't seem big, but turns out to be big in the end. All right. That is it for 2.3. The next lesson will be 2.4, and we're going to talk about limits, and it's going to be a little bit of a longer one. There's a lot that we need to discuss in 2.4, but it'll be really the start of our calculus topics. Usually when I teach the Calc 1 class, 190, we start talking about limits like day one. So it was kind of nice that you all got a little bit of a buffer here to have a little bit of algebra review before we got into the heavier calc topics. So I hope you really enjoyed this mathematical models section. Now you get to enjoy writing your own models on your homework. So have a wonderful time with that. Let me know if you have any questions.